Good evening, everyone. Thank you for coming for today's talk. It's my pleasure to invite Dr. Tan give us a talk on the topic of data-driven mobile endpoint security. Dr. Tan received a PhD degree in computer system by University of Technology, Sydney, Australia in 2014. He now is an assistant professor in the School of Computing at Edinburgh University. Before coming to Edinburgh, he held 3 different research positions at 3 different universities. Dr. Tan was published over 70 quality scholar publications in the highly cited IEEE transaction computing and highly cited IEEE transaction on sensors. He is recipient of Science and Technology Award, National Research Award from the Research Council, and the Best Paper Award from International Conference. So let's introduce Dr. Tan for the talk, and Dr. Tan, the floor is yours.
Thank you, and thank you for BCS Edinburgh branch giving me this opportunity to talk tonight. So first of all, I would like to welcome everyone joining my talk on data-driven mobile endpoint security, detecting malware and unauthorized access. So the talk was developed based on the recent research outputs of my research team in Edinburgh Napier University. And for today, this talk will show you what endpoint security is about and why it's important, and what major mobile threats and vulnerability cause critical challenges to securing mobile endpoints. And finally, we will present our recent proposed defending mechanisms. And as you know, by definition, the endpoint security vary among leading vendors in the security space. But essentially, endpoint security addresses the risks presented by devices such as mobile devices, laptop, desktop PCs connecting to an enterprise network. And the concept is being expanded to all kinds of network environments as the accessibility and involvement of mobile devices in our daily life. Due to the rise in mobile threats, the need for effective endpoint security measures has increased substantially. And with our employee relies on mobile device and home computer and laptop to connect to company networks and conduct businesses, a centralized security solution is no longer adequate or enough for today's ever-shifting and undefinable security perimeters. So I believe nowadays we use mobile devices very often, especially your mobile phone, for banking, shopping, social networking, education, and mobile working. So especially during the COVID-19 pandemic, people has tried to use all the different types of mobile devices to enhance the productivity. So this become a big issue because we are not staying in the company with the well-defined security policies and measures in place, and we are working remotely from home. This become a bigger issue for your employer to make sure you have the correct defense on your end. So by using the centralized security solutions is not enough. And things has gone worse, as you know, due to the COVID-19 pandemic in quarter 2020 alone. And we can see this has significant increase of the threats every minute. So in the first quarter of 2020, about 375 threats per minute, with a 70% increase in mobile malware as compared to the quarter 4 2019. And the number is getting bigger and bigger now in 2021. And these threats particularly target employees working from home due to the COVID pandemic. Nearly 1 million COVID-related malicious files detected, affecting about 4,355 organizations. And more effective endpoint security measures are in increasing demand, particularly considering the rise in mobile threat. They supplement centralized security measures with additional protection at the points of enter for many attacks, as well as the points of egress for sensitive data. But by requiring endpoint devices to meet security standard period to being granted network access, enterprises can maintain greater control over the ever-growing numbers of access points and more effectively block threats and access attempt period to enter. So beyond simple controlling access, endpoint security tools also provide capabilities such as monitoring for and blocking risks and malicious activities. So as we can see, we need to have security measures on end devices to help identify any malicious payload or files on our endpoint device, and also secure these and block any malicious attempt to making use of our handheld devices as a stepping stone into the company network, the corporate network. And the recent statistics shows malware, ransomware, and loose theft took 3 seats among the top 4 mobile threats, which need prompt reaction to address these security challenges. And I think ransomware is definitely one of the terms you've been hearing for a long time. And malware basically is a very big groups of malicious software, and these has been in the digital world for a very long time, but still until today, it remains to be an important threat to our computer security and network security. And loss of faith is also a big threat for now. And you can imagine if your computer or your mobile is stolen, the sensitive data in the mobile will have a chance to be extracted by the malicious player. So have your data encrypted is important, and it has been done by many of the mobile vendors. But have you ever think of your mobile phone, if left on the table, you forgot to lock the screen, and people might pick it up and continue doing something on your mobile, your access, the mobile you have access to, and they doing some online transactions on your phone. This might cause even more harmful impact financially, and also they can steal your personal information if you forgot to lock the screen. And the current approaches is not good enough to defend these kinds of attack. So I will give you more information later and tell you the approach we developed to secure your mobile. And then let's back to the malware. In the mobile endpoint security, the first threat, the top priority we have been given to tackle this threat is to the malware. So malware is a particular worrisome software, is intentionally created to harm data and resources in a computer. They can disrupt the entire functionality of a computer system. However, to defend against malware is a big real-life challenge, as an overwhelming numbers of new malware appear on a daily basis. It's very unlikely for human experts to catch up with the pace of the development of new malware. And even more challenging obfuscation techniques have been employed to build malicious binaries to prevent detection. And these techniques often involve packing the malware, transforming its static binary code, and or transforming the dynamic binary code of a malware. And in malware packing, a packer compresses, encrypts, and or modifies a malicious file format, and all these tricks decrease the chance of detecting or the malware by anti-malware products. So a packer, as you can see in the diagram, a packer can be made this analysis by the security staff is more harder and increase the amount of time required for analysis. So if in the case, this packer is to encrypt or compress a file, a stub is a piece of code that contains the decompression or decryption routine, acts as a loader which executes before the malware, and during the compression and the encryption, the original file is parsed in the packer routine and stored in a pack section in the new exe file. And once the file is run, the decompression stub stored in the pack file will decompress the pack section, and the original exe file is then loaded into the memory. So by doing this compression using the packer, it would definitely increase the difficulty of analyzing the malware. And of course, in the wild, there's more than one type of packer, and some other packers combining with the techniques such as anti-debugging and anti-sandbox, and to make this is even tougher for the malware analyst to do is analysis. Besides, polymorphic and metamorphic malware are both capable of changing themselves as they propagate. So a polymorphic malware uses a variable encryption key to change each copy of the virus, the malware, and metamorphic malware is capable of rewriting its own code while maintaining the functionality. So the big difference between the polymorphic and metamorphic malware is the polymorphic malware use variable encryption key to make itself looks different in each copy, and the metamorphic malware is doing a different approach, using a different approach, and to change, to mutate its code instead of using an encryption key to change its appearance. So malware have the capability to change its code itself automatically. This is a kind of metamorphic malware. And since the current analysis and detection techniques are mostly reactive and therefore cannot detect unseen or obfuscated attack vector, so this is the big challenge for mobile security experts to tackle these kinds of malware. And among of these obfuscation techniques, metamorphic malware, the metamorphism, appears to be the most sophisticated ones, as it can change its appearance and change its code, entirely in each copy. So this makes signature-based detection very difficult. And if you, by chance, can extract a piece of unique byte code from the known malware, this will not be practicable, will not be useful to detect the new copy, because the new copy changes itself. It looks different, and these unique signature cannot be found in the new copy. So for the metamorphic malware, how it mutates itself, how it changes itself, it normally uses the following 4 mutation techniques. The first one it uses is instruction substitution, and this involves the replacement of an instruction set with a valid and distinct set which serves the same function. And then secondly, it can insert garbage code, and this works by inserting junk instruction into the original program code, and the garbage code has no effect on the functionality of the code, but just change the code's structure. So makes the structure of the new copy different from the original. So the approach can particularly distort the opcode-based analysis approach. And the third technique has been used is the variable substitution. And this is also called the register substitution. And this is when a malware replaces a given memory address known as a variable with a different but valid variable without alerting the code's function. So it's just basically, you can think that way is you have a variable A, you change the name to X, Y, and Z. So this is variable substitution. And then the last technique has been widely used is called control flow alteration. So this is a technique and to change the flow of instruction, and the code structure are distorted significantly. And this is done through the insertion of meaningless loop instruction, which do not distort the order of the instruction execution at runtime. So when it runs, the order of the code will stay as it is, but when you look into the static code itself, it looks different from the original copy. And then metamorphic malware binaries has various layers where they can mutate. So by using the technique we mentioned previously in the previous slide, and it can do mutation on the network layer, application layer, or exploit layer. And on the network layer, basically what it does normally is it will use different types of networking protocol and IPv4, IPv6, and even some other legacy network protocol in each different version and in different environment. And for the application layer mutation, it will normally try to exploit the application layer protocol's vulnerability. So say for example, the protocol runs, this approach is to enable the multiple processing of sections in the application layer over one connection. So make use of one connection to serve multiple sections in the network. And in the protocol runs, from most of the network-based intrusion detection system, it will only check the first run and to make sure this is legitimate, and then it will not check the subsequent runs. So in the subsequent runs, so it's runs, and this will not be monitored. So every time if the malware, the metamorphic malware, try to change the first run, the content in the first run, there will not be any signature from on the network-based intrusion detection system be able to detect it, because you will use different content in the first run every time. Okay, and then for the exploit layer mutation, and these types of mutation is applied to the attack rather than the network section. So it uses the previous mentioned techniques, the 4 techniques, to mutate the code, the source code. So this makes it even harder to detect. So as metamorphic malware are very dissimilar to, and also too many variants to keep track of, and more importantly, we do not know what the next generation, the next new copy will look like. So these types of malware normally go undetected. And also the scary story is nearly 100% of new malicious program discovered in the recent years is from the Android platform. So that gives us a good reason to put our focus on mobile platform and Android operating system. And the current metamorphic malware detection mainly use 3 detection strategies. So signature-based is a very well-known one. I think most of the attendees, if you're working in the domain of security, working with antivirus, you will know most of these antivirus engines, they use signature-based detection. So you have to keep updating your database, signature database on daily basis to make sure you have the up-to-date signature to detect attacks. So these will involve the extraction of unique byte streams, which define the malware signature, and this involves scanning files in the host machine in order to find a given malicious signature. However, as we know, they often not efficient in detecting advanced malware like metamorphic malware because it changes its appearance, changes the code in each copy. So it doesn't work very well. And this other approach, people or security vendors and trying to take or advocating this will be the next generation cybersecurity intelligence. That's the heuristic-based detection. These, as we know, is give the focus onto the behavior of the malware instead of a piece of static code. So these detection techniques will involve the analysis of behavior, functionality, and characteristics of suspicious files without relying on the signature. And unlike the signature-based detection, its goal is not to discover a given signature, but detect the malicious functionality of the malware. So this method normally use data mining, machine learning, and some of you might know about deep learning. This is the chain. We try to make use of the huge amount of data to collect knowledge and learn the knowledge from the huge amount of data to build a more intelligent system. So these are the fundamental techniques or the base of heuristic-based detection approach. These algorithms, of course, has its vulnerability. If you have studied this field and you know machine learning itself has vulnerability, security vulnerability as well. So even though it can help to secure our network, secure our computer, but itself is vulnerable. It's vulnerable to adversarial samples, and you can generate adversarial samples to evade the detection of a machine learning driven detector. So this is a problem we should think about and to solve when we develop a heuristic-based detection system. So try to use machine learning, help to automate the intelligent detection, but also don't forget to stop this vulnerability affecting the security of the detector itself. And then the last approach people have been trying to use is called malware normalization and similarity-based detection. This is a system that takes an obfuscated executable, undoes the obfuscation, and outputs a normalized executable. The level of code obfuscation determines the effort we need to normalize the metamorphic malware. And so more sophisticated transformation could seriously undermine the effectiveness of the static analysis using malware normalization and similarity-based detection approach. And as we can see from these slides, and you probably can sense, from these three, the heuristic-based detection strategy shows the most encouraging performance in targeting or handling the metamorphic malware because it has the capability to use the behavior to find out the suspicious file instead of relying on the static code. But also, this heuristic-based strategy is data hungry and prone to adversarial inputs. So when we develop an approach, a detection system using this strategy, we need to take this into consideration. But this is not something very easy to solve. So this also the main reason we would like to carry out our research on this topic in this area. So by knowing these issues, we would like to think a new strategy to develop more robust defending systems. Our observation from our study on this topic is that an adversarial learning techniques appear to be one of the most promising weapons to win this battle, and deliberately feeding machine learning model underlying the heuristic-based detector with malicious input, that's the adversarial samples, and could help discover loopholes and subsequently improve detection models to be more robust to attack. But you can see the problem is it's really hard to get a high quality adversarial training data, which can present the current state of the threat and provide a rational, precise vision to the future threat landscape. So even though you can collect good samples, the known samples, but how we can predict what happened in the future? And without knowing what happened in the future, or without being to predict what is going to happen in the future, this is really hard to give your machine learning model some good knowledge to try to run, to win this running and win this race, and to get in front of the malware and to stop them from propagate. So that's the things we need to consider. And lucky enough, we have solution already. So this solution, potential solutions available, is based on evolutionary algorithms. So the evolutionary algorithms are potential solutions to this issue because they have shown effective in code optimization, which can be considered a similar problem with a different objective in contrast to adversarial software sample generation. And given a quality function that needs to be optimized, a population of randomly generated potential solutions to the problem is first created. So the solution are selected for reproduction in a manner which is biased by their fitness. And then a reproduction operator generate new offspring from the selected solutions by applying processes which mix information from two or more solutions. So this is called crossover. And by a mutation process that makes small random changes to the solution. So by doing that, we can evolve the samples, the data, and make sure the new fitter solutions replace the poor quality ones in the population. The population gradually become more fitter. So this is the well-known theory of evolution. So gradually to combine the best, the fitters, and generate the even better solutions in the future to evolve to generate the best solution. And the advantage of using evolutionary computer can be concluded as the follow. First, the evolutionary algorithms can provide an exploration of huge search space, which is one of the challenges to be solved in searching for covariance. And then it provides a good provision of operators that enable easy manipulation of code. And then it can also has been also proved its ability in transformation and optimization and improvement of software code. So by taking all these similarity between the two problems and the advantage of evolutionary algorithms, and we have the confidence, and these will be a good potential solutions to help us to generate adversarial samples for machine learning model to use for training. And based on this motivation, based on this observation from our preliminary study, and we propose to use the evolutionary algorithms to create variants of malware that are diverse and also as evasive as their parents' malware. And as such, improving machine learning models with augmenting training data that contains new variants provide a rational predictive vision to the future threat landscape. And even though there are some work has been done and using EA to create test data and create training data to enhance the performance of the detection of metamorphic malware, but they are not perfect and they do have problems. And some of this work try to solve the problem by taking very simple finish function. So they're only considering how many detection engines and their newly generated sample can evade. But the second problem is they do test it with the major antivirus engine. They test their variants on their engine, but they are not sure whether this evasive sample, newly generated evasive sample, are actually still malicious or not. So they can evade detection, but they never try to test it in the real environment, never run them, never be sure whether this sample generated can do exactly same as the parent malware. So based on this observation, and we know we need to define a well-informed finish to govern the evolution and make sure the diversity of the malware variants could be whole. And in this context, a finish function is how to help discover new evasive variants that are significantly dissimilar from the original malware in terms of the code structure and the behavior. So we want to make sure the newly generated copy, or we call mutant or variants, they structurally and behaviorally different from the original malware. And then taking the objective and requirements into consideration, we develop a new evolutionary algorithm, and which in this algorithm, we employ a canonical model of an evolutionary algorithm and return the single best mutant found at the end of each run. So please bear in mind in here, we use evolution algorithm, the new evolution algorithm, to generate the new mutant, but we only acquire the best mutant at each run. So you can imagine if we want to generate multiple mutants or variants, new copy of the malware, we do need to run multiple times. So you can imagine this is quite time-consuming approach. So please bear in mind. And this is only our first work in this domain and trying to use evolutionary algorithm. So we have solution later on. So you can see the algorithm and the code with the pseudocode we presented in the slides. And in the initialization stage, to create an initial population of mutant, a single mutation operator is applied to the original malware, and the mutation operator is chosen at a random at a random basis and apply exactly once. And this process is repeated to create P mutants each time. So during the initialization, we need to set a numbers of mutants we want to obtain, and we choose only one mutation operator to do the mutation and generate P mutants we need. And more specifically, in this work, we use 3 operators: instruction reordering, garbage code instruction, and the variable swapping. So these are the 3 operations we have considered in this work. And then towards selecting filter parents to create offspring from them, we use a standalone operator, and two-element selection have been employed in this work. So this selection operator has been chosen because it can be easily tuned to various selection pressure. So in two-element selection, the population is stored and k potential parents are selected at random. The best parents among the k prospective parents is selected to be combined to form children in the next iteration. So we choose the best parents and combine them and to use them as the point to generate new mutants in the next iteration. And the finish function we use in this work, and we consider 3 finish values in the work. So the first one is called detection rate. So these returns a value between 0 and 1, with 0 signifying that no detector recognizes the mutant. And the second finished value we consider is the behavioral similarity. This returns a value also between 0 and 1, and which compares the behavior signatures of the mutant to the original malware, and which 0 indicating maximum dissimilarity. And the last finished value we use in this work is called signature similarity, and also is ranged from 0 to 1. And again, 0 means they have significant difference from each other. And then if a mutant is deemed not executable, then the finished value, the total finished value, we set to 0, set to 1, and regardless the measures metrics or the finished functions used. So please bear in mind this is the work. This is something has been introduced in our work to check the executability of the newly generated mutant. This has not been considered in the other related work. So this is one of the new aspects of applying evolutionary algorithms in malware sample generation. And then these are the things we have been trying to use in this work to help us to generate new mutants, quality mutants, to provide training data for machine learning model to learn from. And then to examine the influence or the finished functions on evasiveness, and we conduct the following experimentation. And each of the finished functions was involved in a 10-run mutation to evolve new variants from each of the 3 different malware family. So the malware family we consider in this work include the Ducklick and Joy Kung Fu and GG Checker. So there are 3 malware families we can acquire from the internet, and they are the real Android malware. So we try to use the real Android malware and generate the offspring of this Android malware using our approach. So the results are shown in the table. So in the table, you can see in the case of duck-lick, the structural similarity function provides the best result and produce 10 executable variants. And the other two finish function both produce 7 variants. And for the other two malware function families, detection rate finish function does the best job, and resulting in 10 and 9 variants for Joy Kung Fu and GG Checker. And while down to the second experiment about evasiveness, the result shows that new variants are much more evasive than the original malware. And the variants generated using the detection rate finish function are more evasive than the other results from the other two functions. So this is the data. So you can see that the newly generated mutants are more evasive than the original family, the sample from the original sample from the same family. And again, down to the detection rate finish function, this shows promising in bringing in diversity in terms of detection signatures. And what is the detection signatures we meant in here is the records of the malware engines that successfully detect the variants. And higher resultant values means higher difference between the sets of malware engines detecting distinct malware variants. The result of the experiments of behavioral signature shows a high diversity in all 3 families, even none of finish function is dominant. So you can tell from these tables. And then while evolving using the structural similarity finish function produce mutants that are dissimilar to the original malware, its advantage to generate mutants that are structurally dissimilar to each other, and it can provide the maximization of diversity in the training set. And this is typically important because in the training set, we want to include as many as different types of code, different appearance of the code, function the same as possible. So the diversity is the things we have to take into consideration very seriously, but this has not been considered in other related work. So you can see that the pairwise similarity between each pair of the mutant shown in this in this diagram, and it produced by the finish function for all the malware families. And this gives a score between 0 and 1. And where 0 means the pairs is completely different, and 1 means they are exactly the same. So if you look at the scale, the color-coded scale shows you towards to the yellow. It means they are exactly the same, and towards to the red color, it shows they are very different from each other. So the color-coded grid is then plot, and as you can see, we plot 3 in this slice, and representing the similarity scores of each pair as seen in the figures. And it can be noted from this figure that the finish function that produce the most structurally diverse variants is structural similarity function, and for the GG Checker family and duck-lick family. And then the finish function produce the most structural diversity variants for Joy Kung Fu family is a behavioral structural function. So it's different from the previous 2 families. And in this case, the behavioral structural function gives the best performance in terms of diversity. And it's very interesting to know at least the structural diversity variants are produced by Dudley family, and the most structural diversity variants are produced by the Joy-Kung-Fu family. And as we can see from the result, we can summarize that evolutionary algorithms can be used to create a suite of malware mutants that are more evasive than the original malware. And also, these mutants are behaviorally and structurally dissimilar to the original malware. But definitely, there's some limitation. As we know, the EA algorithm generate only one new sample in each run, so it's very time consuming. And how to speed up this process, and we'll need to introduce a new approach. And the new approach is called Maplet. So we introduced the Maplet approach into the follow-up research work, and to address the slow generation issues, and also try to give a better guarantee to the diversity of the samples. And then the Maplet, why we choose Maplet, just because Maplet can discover high quality instance with varying behavioral characteristics within separate shells in the behavioral grid. And given various features of a solution represented as the behavior space of the solution, the algorithm seeks to find zero diversity behavior space of that solution, while ensuring that each behavioral space has a solution with the best performance for the given behavioral space. By introducing the Maplet, and we improve our algorithm, and the new algorithm has been changed, and now with the Maplet into consideration. So in here, the algorithm begins with the generation of initial solution at random. The feature vector of the solutions are calculated and mapped to an archive. And then only the most elite solution, so the best solution found so far based on the objective function, is stored per shell. And then until the algorithm finish, a random genome is selected. A variation operator is applied to the random genome, which is evaluated and placed in the grid only if the shell is empty or is better than the current occupant. Otherwise, it will be discarded. So again, same to the previous work, and we consider only 3 mutation operators in this new algorithm, and they are the garbage code insertion, and structural reordering, variable renaming, or substitution. We can say that. And the result shows according to the experimental setup is given in the next slide. And the result from the new algorithm managed to find more diverse solution in all 3 cases. So when you compare the first algorithm and the second algorithm with the Maplet, and you can see on the left is the first algorithm, and the Maplet, the result of the Maplet is on the right. And you can see there are more shells are now occupied by different variance samples. So this is quite consistent across the 3 families. And here is a table, and the table shows the median results obtained for the 4 evaluation metrics. They are the performance, coverage, reliability, and precision on the dataset, on each dataset. And the value in bold indicates the best performing algorithms, where the difference between the median is significantly, is quite statistically significant. The Maplet outperforms the first EA algorithm in general. So as you can see, the Metamorphic, in most of the cases, it takes the lead. So we can see that Metamorphic performs better than the first algorithm. By far, we have been able to produce diverse evasive variants of malware, but we still have a question here. And can classification of metamorphic malware be improved with this generated malware variants? So here is our question. So we try to answer this question by taking more experimentation with the well-known, well-received machine learning algorithm and see whether this algorithm can perform better with the newly generated data. So the algorithms we use, including logistic regression, support vector machine, naive Bayes, decision tree, and k-nearest neighbor, and LSTM. So to do this test, we divided the whole set of data into 4 subgroups. And the first group contains the benign samples. And the second group contains the malicious samples from the internet, from the web. And the third group contains the evolved malware. So the evolved malware generated by us using the algorithms. And then the last group is the test group, is the evolved malware not being used for training. So let's take a look at the final result. So after we conduct tenfold cross validation, we can see that by training by the dataset benign and the web sample, and shows all algorithms achieve exceptionally high validation accuracies and above 90% for all the test algorithm. And while the results of the tenfold cross validation of the model trained using the benign and the evolved sample slightly decreased. So the decrease only happens to the k-nearest neighbor and the decision tree and the support vector machine. But linear regression and naive Bayes were made constant. So as you can see, this naive Bayes and linear regression were made constants. And then the results from the final tenfold cross validation of the model trained with the benign sample, the malware from the web, and the evolved sample shows good validation accuracies for all the algorithms as well, and none of them is below 90%. And the naive Bayes is the most stable algorithm, achieve 95% constantly across 3 tenfold cross validation. So by taking this evaluation, we know naive Bayes is the most stable one. And finally, we use the best trained model and to compare against a well-known deep learning model, that is the LSTM, in the further evaluation against the unseen evolved malware. As you can see from the table, the accuracies of the both algorithm in detection of future malware are improved significantly after being fit with our evolved variants. And this demonstrates that our observation hold and the adversarial learning does help improve the robustness of malware detector. And evolutionary computing plays quite significant and positive roles in conducting high quality predictive malware variants describe the future threat landscape. So this provides good information for the machine learning algorithms to learn from and to detect the unknown variants. And then apart from the malware, we still have issue, as we mentioned before, is the access to the unlocked cell phone. So how to solve this problem is very important challenge to the secure endpoint, mobile endpoint security. And as you know, the conventional or the traditional authentication approach we use on our mobile mainly rely on password, challenge, face recognition, and fingerprint. And please bear in mind, they are one-time authentication. So what happened is you authenticate yourself once, and if you keep your mobile open, you do not switch it off, or you do not lock the screen, it will accessible by anyone else, and there's no further authentication will be done. So this is a significant vulnerability in security, in mobile security. And what we are trying to do and how to solve this problem is we try to use a behavioral biometric driven solution, and to authenticate user while they perform the basic navigation steps on a touch screen device. So think about, you have a touch screen device, that's your mobile, most likely. And when you use a mobile, you swipe your finger and up and down from left to right. And by doing this intuitive movement of your finger, you'll be authenticated. And this has some advantage is without any dedicated and explicit security actions that are required attention from the user. So you just do the normal browsing and you will be authenticated continuously. And then the main hypothesis is continuously record touch data from the touch screen is distinctive enough to serve as a behavioral biometric. So everybody has, when we use a cell phone, we have a different touch behavior. So this is the motivation behind and the main hypothesis. So my touch behavior will be different, it's different from yours. So I can be identified or authenticate by my own behavior, touch behavior. And these are some data we collected on mobile. And as you can see from the different users, they have a different touch behavior. So this gives you some sort of confidence to tell this is something worth trying. And then there are two actions which trigger the system locks the fingertip data. And first is sliding horizontally over the screen. And usually one does this to browse through image or to navigate the next page of icon. And the second trigger is sliding vertically over the screen to the next screen content up or down. So this is typically done for reading email documents and web page or for browsing menu. So you can see by taking the vertical and horizontal screen finger movement, and we basically cover almost all the activities we will do on our mobile can be used for authentication. And then the continuous authentication, it only changes once and during you set up your mobile. So once the classifier is trained and the device begin to authenticate the user, and during this phase, the system continuously checks all strokes, and the classifier estimate if they were made by the legitimate user. And then for consecutive negative classification result, so if it consecutively detect the behavior is different from the recorded behavior, then the system will restore back to the initial entry point based authentication, and it will challenge the user. And then this is the preliminary work we have done. And if you are interested, you can read the paper from recent paper from us, but there's still some open questions to be answered. And in the related work, we have seen other researchers, they try to use multi-class classification and bi-class classification, but this is arguable. And as you know, with the GDPR in place and also the personal data regulation, how is possible to collect others' data to train a classifier to identify you or classify you apart from the others? This is very difficult. So even do by class classification is not easy with the current data regulation. So to our best knowledge, the single class classification will be more feasible, more doable in this kind of practice. And also, and how to protect the user privacy is something we have to take into consideration. And we have our behavior recorded screen, the fingertip data collected. Do we want to share this data to the cloud for process? And I don't think so. So you want to store, if you want to use it to create an authenticator for yourself, for your mobile, you would like to keep this on your mobile phone instead of sharing with others. So federated learning is something we should take into consideration, and homomorphic encryption is also a good protection for us. And then to make your model train on one device can be used on another device with a different screen size, perhaps, or a new device with slightly different specification. Transfer learning will be very useful. So you transfer one model train on device A and move it to the device B, and with fine-tune, it can significantly reduce the time of training, retraining, and make this is almost ready for use. And this is some open questions I leave here and for you to think about, and some of you might would like to do some research on this topic. And I think these are quite good open questions to tackle. And these are the references I have used for this presentation, and also some of the published work we have made, and I have also included in the slides. And if you have any questions, please do not hesitate to ask now or send me a question later. And these are my contact details. So this is my homepage and my email. So you are more than welcome to ask any questions. Thank you.
Thank you. Thanks, Dr. Tan. That's full of, there's lots of information here. I think it's good to say how the security experts are really packing up themselves to fighting for current IT security issues. I think we are going to take some questions from the audience. The format we're going to use is actually you put the hands up and I will allow you speak. You either can speak from your end or you can type in your question from Q&A. I think so Dr. Tan, I have one immediate question come here is do you want to share the recorded presentations with all the participants?
Sure. I have no problem.
Okay,
yeah.
So I think our BCS Edinburgh branch will be able to upload this on the website. Okay. Right. Can speaker show again the slides of reference? Okay, so we'll have the question
sure.
from the audience. Yeah.
So you're more than welcome to take a screenshot if you wish.
Okay. As I said, these slides will be available to download on the Edinburgh website, and also these recorded sessions. So if you need more time to digest it, you can go back to the our website, Edinburgh BCS website. There is downloadable recording for you as well. Right. So we wait to see if any more questions. I have a question coming to you, Dr. Tan. It's a question from Wahan. So what's a good antivirus software or platform for mobile devices you can recommend?
This is a tough question because most of these antivirus software, they will most likely share the similar approach for mobile malware detection. So they mostly rely on signature based. So whether good or bad, mostly depends on the signature, the quality of the signature. So this is a quite tough questions to answer. So for me, I do see there's a big gaps to be improve the quality of the antivirus services.
So I have another question. Thank you for answering that. Yeah, I have another question coming to the chat box. Is how long does it take on average to gain enough information to recognize end user pattern on mobile device?
On the mobile device, normally you need to have at least, let me see. If you are thinking about just give a quick test, and there will be several exercises. Let me see the research we have done. We use the minimum data is around 200 joules. So by using 200 joules, you can develop some meaningful model for user authentication. But of course, the more joule you collect, the higher will be higher accurate of your model. So 200 joules some sort of minimum, we can achieve some discernible results.
Excellent, thank you. Okay, I think I have one question. I'm going to try to understand for this meta malware detection method. So you try to use the evolutional algorithm, and you mentioned the evolutional algorithm actually quite time consuming. By the time you generate the mutates, maybe there's another new type coming. Really, the question is, when you use evolutional, you have your parents, and these parents from the 3 data set you choose. So how are you able to include other variations which haven't seen before?
And we do not necessary to include a new generation. And in this work, we are trying to demonstrate the possibility use evolutionary algorithm to predict the future. So we take one sample. So initially we take one sample and try to evolve it by using evolution algorithm to predict the most most possible variation in the future. So as you can see from our research work, we try to consider the diversity, we try to push the diversity of the new generation as much as possible. So that is trying to cover the full spectrum, if possible, to gather more information, more knowledge for the machine learning model to learn. And the reason why we think this is approach as doable approach is just because we have the finish function to guarantee all these mutants, they are executable. Because if we use evolutionary algorithms to generate random things, it's possible to generate millions of samples, but not all these samples are executable. And as you know, if the new variant is not executable, it's not harmful. So by taking this into consideration, we can narrow down the numbers of future mutants. And of course, if we can take some new variants of the same family into consideration gradually, then this will become a more strong or more valuable data set for the future development. This is a process we can gradually improve, but we don't need to do it all in once.
Okay, excellent. Yeah, okay. One last question. I mean, since I haven't, we're still waiting some audience digest your talk right now. One last question is, as a recent news talking about the spy on your phone. So it's something called spyware, spyware.
Mm-hmm.
Yeah. Are they similar type of malware, and how you actually can counterpart of this malicious software?
Spyware, you can say spyware is a kind of malware, and it can be turned into a kind of metamorphic malware, because the definition of metamorphic malware is it can change its code automatically. So it can have it can bear different purposes. It can be a ransomware, it can be a spyware, can be a Trojan horse. So these can be done by using behavior analytic. So you can see if a spyware will most likely trying to access to, if it's trying to record your typing, it actually will do some typing recording processes if you're trying to record your voice and listening you behind the screen, and this will activate your microphone. So if we have a detector and monitoring the usage of the different resources on the mobile, and we'll be able to identify it.
Excellent, thank you.
You're welcome.
Let's wait a couple more minutes to see if any more questions. I think I have to say it's a really excellent talk and so many information here, and it's takes a lot of time to digest. Yeah.
Thank you.
I have one more question come up. No, not really. Yes. Oh, yeah. So there is one more question come up from Olivia. When you are trying to predict that future mutant, does that mean you might have a new mutants that hack may not use, but at least you can be prepared?
Yes, exactly. That's correct. And because we don't know what sort of new copy will be generated by the hacker, so we try to generate all the possible candidates. So we will like to prepare ourselves to defend against any sort of new mutant, even though this may not happen at all. But we want to arm ourselves, to equip ourselves with the strongest defense mechanism to protect ourselves against this any potential attack.
Okay. Okay, excellent. Yeah, with audience feedback, it's very interesting, and thank you very much.
Yeah, thank you so much, and I'm so delighted you like this talk.
I would like to say now we close this meeting, and I know we are in virtually, but I just have virtual round of applause to Dr. Tang, and thank you for your time, and thank you for this excellent talk today.
Thank you so much for giving me this opportunity to have this chance to show you the work of our team. I would like to give my personal appreciation to my research team, my PhD students. They have done a great work to make this happen.
Okay. Okay, we close meeting now, so you can leave when you have time to do so.
Yeah. Thank you.
Bye now.
Bye now. Bye-bye.
Bye.